In the 1960s, we launched our first gamma ray observatories. Now, these were not actually developed to look for gamma rays coming from space. These were actually spy satellites. At the time, the only thing that we knew of that gave off gamma rays were nuclear weapons. So we were looking for the signatures of nuclear weapons testing. Essentially, we were spying on the Soviet Union. Well, just a few days after the launch of the first gamma ray observatory, we actually detected a burst of gamma rays, which led us to think, oh no, the Soviet Union is testing nukes again, when at this point we had agreed to not. And fortunately, somebody realized that the way that this observatory worked is that gamma rays coming from the Earth were actually detected in the same way as gamma rays coming from space. So after doing some rejiggering, they realized that this was actually a space event. Something from space was giving off these gamma rays. Now, as we continued using these gamma ray observatories, we found more and more gamma ray bursts coming from space. Now, in this image over here on the right, on the bottom, this is a Milky Way view. So right through here along the center, this is an all-sky view with the Milky Way running along the center. This top one is the exact same view, but now pinpointing where the gamma ray bursts are coming from. Notice that they're coming from everywhere. They're not just coming from the disk of the Milky Way. Now, it could be that these things are coming from the halo. This is the region that surrounds the Milky Way. Okay, so maybe out in the halo something is causing gamma ray bursts, or another possibility is that these are actually coming from very deep space, from very, very distant objects, like other galaxies or so on. Now, unfortunately, just knowing their position on the sky doesn't actually give us any information about how far away these could actually be. Here is our fifth lecture quiz question. What is a Type 1c supernova? A. Core collapse of a supergiant. B. Core collapse of a red giant. C. A white dwarf beginning carbon fusion. Go ahead and think about it, and we'll discuss in just a bit. Alright, so what is a Type 1c supernova? It is A. Core collapse of a supergiant. Red giants never get big enough to go through core collapse, so this just isn't a thing. And a white dwarf beginning carbon fusion, that is a Type 1a. So the correct answer for this is A. Core collapse of a supergiant. Well, as we advanced in technology, we began to be able to pinpoint where in the sky the gamma ray burst was happening fast enough and accurately enough. We were then able to go and spot a visible counterpart. When we did, the visible counterpart was always associated with a distant galaxy. In other words, gamma ray bursts are absolutely not coming from our Milky Way, even out in the halo. In 1997, there was a group of astronomers who were able to find the visible counterpart fast enough, within just 30 minutes, that they were then able to take the spectrum of it. And, based off of the spectrum, they found that it was a Type 1c supernova. Now, since that time, we've been able to take the spectrum of other gamma ray bursts, and they all seem to be a Type 1c supernova. However, the problem is the amount of energy. If we assume that the energy of the supernova is going in all directions, then, so take the amount of energy that hits the Earth, and then add up together how much energy that would be in all directions, then these gamma ray bursts would actually have way more energy. Specifically, a gamma ray burst would have as much energy as 100,000 supernovae. Okay, so this is a problem. We look at it, we get the spectrum, and it's a Type 1c supernova, but based on the energy, it has enough energy as 100,000 supernovae. Something really weird has to be going on. So what we think is actually going on is all of that energy is not going in every direction. Instead, it's actually being beamed in a jet pointed at us. Okay, so specifically what we believe happens is we have a supergiant star that then goes through core collapse. As that core collapses, it generates a black hole, and as material falls onto the black hole, it creates an accretion disk with a strong magnetic field. That magnetic field will then generate these beams of light similar to what we talked about with a neutron star. Now, if it's pointed directly at us, then we're in line and we see a gamma ray burst. If we're not in line, then we don't see the gamma ray burst and we see just a typical type 1c supernova. If all of this energy is highly focused and beamed, then it reduces the overall amount of energy of the gamma ray burst into the same realm that we would expect for a type 1c supernova.